Okay, so we're going to use differential equations to introduce a new notation. Now, do you see that I'm giving you a differential equation because I'm giving you a derivative? Remember, dy dx is the Leibniz notation for labeling derivative. And so a lot of people don't really care for this notation at first, but you're going to find that you like it better and better and better during the second half of calculus. So that says take the derivative of y with respect to x. So I can simply multiply both sides by dx, and then I have dy equals f of x dx. Now I'm going to introduce this new notation. You see this elongated S shape? I'm going to look at that and say that that's a command that says take the antiderivative. It's called an indefinite integral sign, okay? So when I say take the derivative of both sides, so what do I do to one side I've got to do to the other side, right? Then I can take the antiderivative of both sides and solve the equation. Well, let me show you on this left side where I'm saying the antiderivative of dy. What I'm really saying is the antiderivative of the number 1 times dy, or dy, not times. But when I look at that, what that's saying is take the antiderivative of 1 with respect to the variable y. So what do I take the derivative of in terms of y's that gives me 1? Well, I take the derivative of y itself. That's what gives me 1. So if I had had the derivative or antiderivative of 1 dx, then its antiderivative would have been x, because taking the derivative of x also gives me 1, but I'm working with a different letter. Anyway, that's what's going on technically there. So the antiderivative of 1 dy is y, and the antiderivative of little f of x with respect to x is big F of x plus our constant term, okay? Now, why is this useful? You're going to see on the next slide. Here I've just broken down what I'm giving you, okay? So remember the elongated S symbol right here is a symbol that is called the indefinite integral, and it serves as the command telling you take antiderivatives. The little f of x is the part that I'm integrating. Integrating means taking the antiderivative of, and I call that the integrand. Dx for right now is telling me to integrate with respect to the variable x. Now, in Calculus 1 and 2, if you have f of x, it'll be followed by dx. So those letters will always match, the x's will. But when you get into Calculus 3, multivariable, I could ask you to take the antiderivative of f of x with respect to a different letter like y. And that's really cool. That's Calc 3, though, so you're not going to be there. When you get there, again, that's called multivariable calculus. So I know that the antiderivative of little f is big F, so big F is the antiderivative. And I know that I add c to get the general solution, essentially. So that's the constant term. So antidifferentiation is the same as indefinite integration. So we've talked about limits, derivatives, and now we're talking about integrals. Pretty cool, huh? Okay, so let's review some things that we know already. We've been primarily focused on just taking antiderivatives using the reverse of the power rule. So when you have like x to the 4th or 1/3 x to the 1/2 or something like that. But let's review some of the other things you know. So I remember that we did trig functions. So I know that the derivative, sorry, computer glitch, the derivative of sine x equals cosine x. That means I can say that the antiderivative of cosine x equals sine x. So I always have to double check these because the derivative of cosine x is negative sine x. So I know I get those negatives when I take derivatives of whether it's cosine, cosecant, cotangent. So I have to kind of be careful when I'm doing this with antiderivatives. But what I'll write is the derivative of, or the antiderivative of sine x. Again, computer glitch, the screen's not writing where I want it to. The antiderivative of sine x is negative cosine x is what we'll write. And I should be saying plus c, shouldn't I? So if you check what I just did, because you might go, wait a minute, you didn't put the negative where I expected you to. If I take the derivative of my answer, the derivative of negative cosine x is positive sine, because it's technically saying the negative of negative sine. And then the derivative of the c part 0. So it does go back to the input, okay? So anyway, I just wanted to mention that because you might feel like, well, that was backward of what I thought you were going to write down. Let me erase this stuff to make more room. So let's review the other ones that we know that are pretty straightforward. So I know the derivative of tangent x is secant squared x. Therefore, you can take the antiderivative of secant squared x and get tangent x, and I should be good and always say plus c. The derivative of cotangent x, I remember, is negative cosecant squared x. So if you have the antiderivative of cosecant squared x, my 2 is kind of hard to read, then I'm going to say that's negative cotangent x. So that's another one where I'm putting the negative where you may not expect. I know the derivative of secant x is secant x tangent x. Similarly, remember that the derivative of cosecant x is negative cosecant x cotangent x. So then I can really quickly produce 2 antiderivatives. So if you have the antiderivative of secant tangent, then I'm going to say that the answer is secant x. And if you want the antiderivative of cosecant cotangent, then you're going to get negative cosecant x. Now, if you remember in the what problem that we did in the first video, we said the derivative of ln x, that's one that I know, and that's 1 over x. So I'm going to say the antiderivative of 1 over x is ln x. But I need to kind of star this. There's a little more to this that I don't want to get into now, but I'm going to sort of refine that in later lessons, okay? So if I'm thinking about logarithms, then I also want to think about exponentials. So do you remember that the derivative of e to the x is just e to the x? So the antiderivative of e to the x is also e to the x. Now, I could also do the derivatives of the arc trig functions. I could also do the derivatives of logarithms and exponentials whose base is other than e. But I want to keep it a little more straightforward for right now. We'll address all those things, just not in today's lesson. So look at 1 and 2. Notice that there's no prompt for what you're supposed to fill in, but I want you to remember, guys, that what you're filling in is, this is a command that says take the antiderivative of the integrand right here. Integrate, do the indefinite integral of the integrand. So I'm going to say, okay, well, the 10x to the 4th term, I have to have an x to the 5th term, and I'm going to have 10 divided by 5. And I'm going to have the x to the 3rd term is going to raise up to x to the 4th. And I'm going to say 6 divided by that 4. The antiderivative of 5 is just 5x, and I'm going to have plus c. I'm going to go ahead and clean up 10 over 5 to 2. I bet a lot of you are already doing that. 6/4 reduces to 3/2. And I'm done with this problem. So this is no more difficult than what we did before. I'm just trying to get you used to the new notation. Now, I don't like the way the next problem is written because it's not written in a derivative ready format, so it's also not written in an antiderivative ready format. So let me say that 6 over the cube root of x would be more simply written as 6x to the negative 1/3 power. Now the next term, the cube root of 6, or cube root of x over 6, would be better written as 1/6 times x to the positive 1/3 power. So just making some small changes. So my antiderivative step in purple is simpler. So I'm going to have 6, and then I'm going to have x to the negative 1/3. I need to add 1, so negative 1/3 plus 3/3 is 2/3. And I'm going to divide the 6 by 2/3. And then I've got minus 1/6. So 1/3 needs to be lifted by 1. So 1/3 plus 3/3 is 4/3. Divide by 4/3. And then I've got plus 7x plus c. That's the easy part. Now let me tell you, I will normally not write the step I just showed you. What I'll do is cut to this next step that I think for me is easier. Once I write x to the 2/3, I know I'm going to divide by 2/3, which means multiplying by 3/2. And then the same thing, I'm going to write down 1/6. I'm going to make a space and write x to the 4/3. And I know that dividing by 4/3 is multiplying by 3/4. So I start to streamline my writing that way. So you'll see me leave this out. I don't do all of this in one step in my head because I'm afraid I'll goof up basic fraction work when I do that. But I do skip the first step and now go right to the second step from here on out. So 18/2 is 9, x to the 2/3. On this one, I see that 3 goes into 6 twice. So that's going to give me 1/8, x to the 4/3, plus 7x plus c. I'm starting to hustle now because I know you're probably getting a little bit of video fatigue. Now, the next two are the same idea. I want you to clean up the integrand and make it more antiderivative ready. So on both of these, oh my gosh, I've got an STD, a single term denominator. And remember, to cure STDs, we separate and reduce. So let me say 8x minus 5 over x to the 1/3 would be the easier way to manage the exponent work. So on the first one, that's going to be 8, and then I'm going to have to say x to the first minus 1/3 is x to the 2/3. And on the second one, I'm going to have x to the negative 1/3. Now I've written it in antiderivative ready form, so now I'm going to hit it with the antiderivative. So I'm going to have 8. Now I know that 2/3 plus 3/3 is 5/3. I know that I would divide by 5/3, which is the same thing as multiplying by 3/5. So now you see me streamlining how I'm writing things. So negative 1/3 plus 3/3 is 2/3, and flip 3/2 plus c. So now I've got 24/5 x to the 5/3, and then 15/2 x to the 2/3 plus c. And yes, guys, your answers are very, very typical. You're going to have lots of these sorts of fractions in them throughout the rest of calculus, okay? So ditto on number 4. The integrand is not in antiderivative ready format. So the first thing I notice is that I could square the top, and that's easy enough. First squared is 9x squared. The second term would be 3x times 4 is 12x doubled. The third term would be second squared is 16. And I'm going to say over x to the 4th, over x to the 4th, over x to the 4th. Now let me put parentheses around my integrand and say dx. So I'm going to continue to make it in antiderivative ready. So that's going to be 9x to the negative 2, 24x to the negative 3, and 16x to the negative 1 using my rules of exponents. I am rocking and rolling through my antiderivative. Slow the video down, pause it, do it for yourself, come back and check it if you want to. So I'm going to have 9 x to the negative 1 power. So I'll just do that. And then I'm going to have, let's see here, plus 24. So it's going to be x to the negative 2 power. Well, that's going to divide in evenly, so I'll write it that way. And then I've got 16 x to the negative 3 power plus c. So when I clean it up, I've got negative 9, but I don't like x to the negative 1, so I'm going to write it over x because I don't want my final answer having a bunch of negative exponents. Minus 12, I don't like x to the negative 2, so over x squared. Minus 16 thirds, and I'm going to make that x cubed on bottom plus c, and I'm done. I hope that you're keeping up and you're feeling okay about this. Remember, meet me in my online classroom if you're not, so I can answer questions and make this feel better to you. All right, so we've got one problem here with trig in it. Expect to see more and more trig and exponentials and logarithms as we go, okay? So I've got sine x over cosine squared x, and I don't have a clue what I'm supposed to do. Like, I don't have any derivative I can think of that spits out sine over cosine squared as the derivative of the input. I don't know. So on these, what you want to do is you want to write it in a more antiderivative ready format. The integrand is not recognizable. So I could change, for instance, like cosine squared x to 1 minus sine squared x. The problem is I still don't recognize what that is. I don't know. I can't separate the bottoms, so that's not real helpful. But watch. If instead of doing it that way, let's rewrite the bottom as just cosine x over cosine x. We did this kind of thing when we did limits. And then I write the fractions as sine over cosine times 1 over cosine. And that's legal because if I multiply out the top, I get back to sine x. If I multiply out the bottoms of the two fractions, I get back to cosine squared x. So it still equals what I was given. Then I'm looking at it, and sine over cosine's tangent and 1 over cosine's secant. Now are you recognizing the integrand? Do you recognize what you can take the derivative of that produces tangent x, secant x? Or what can you take the derivative of that produces secant tangent? Does that sound more familiar? I hope you're saying, yes, Miss Porter, it's secant x. I already know this. So the antiderivative is secant x and then plus c. So I'm trying to tell you that a lot of these, if you work with your trig identities, you'll get it into a form that looks familiar, okay? So I just wanted to remind you, trig identities are all that and more. So we're going to finish with 2 word problems for today. Just 2. Yay. Now, I notice when I read the problem that I'm being given the acceleration of a motorboat. So I'm going to go ahead and write that down and say, well, it's giving me that a of t equals 12t minus 4. And if I read the problem, I know that at time 0, I have a velocity and a position of the boat. And then it asks me to find s of t, which is the boat's position in the water. But we're going to call it the boat's distance from the dock after t seconds. So I want some sort of an equation for s of t. Okay, I'm stuck. I don't have any idea what to do. Wait a minute. Keep in mind that the derivative of position is velocity and the derivative of velocity is acceleration. So instead of working down the ladder, what if we work back up the ladder and use, instead of derivatives, antiderivatives? Well, what is the antiderivative of acceleration? Working up the ladder, you get velocity. Well, what is the antiderivative of 12t minus 4? Well, I'm going to have t squared and 12 divided by that 2 is 6. I'm going to have minus 4t and then plus c. Now, guys, I'm going to have to do antiderivatives twice, so I'm going to get a c value twice. So let's number them c sub 1 and c sub 2 to make them different. So what I want to do, instead of having the general solution for v of t, which is what I've got, I want the particular solution for v of t. So I look and notice that it says at time 0, velocity is 8. That means if you plug in 0 for time, you get a velocity of 8. Oh, so that gives you that C1 is 8. What's that do for you? Well, it tells you that V of t now has a particular solution of 6t squared minus 4t plus 8. Oh, this is good. Now I want to jump from velocity to position. So I remember that the antiderivative of velocity is position. So if I do the antiderivative of left, repeat, do antiderivative of right. So I'm going to take t squared up to t cubed. 6 divided by that 3 is 2. I'm going to take t up to t squared. 4 divided by that 2 is 2. Sorry, computer glitch. Plus 8t plus c. Well, I've already gotten one c, so let me call this new c c2. I want to repeat the red process. At time 0, it says that the position is 15 feet from the dock, so that's the boat's position. So, again, at time 0, the position's 15. This serves the purpose of getting you to C2 equals 15. Guys, I want you to be careful and I want you to always show your work on this, because a lot of students will start to just plug in for the C's because they think it's always going to be that easy. And while a lot of times it is true that we plug in 0 for the T's, and finding the C1 or C2 is exceptionally easy, don't get lulled into a false sense of security, because they could just as easily say, okay, I know 2 seconds after the boat starts to drift from the dock, the position is, and then you wouldn't be plugging in 0 for t, you'd be plugging in 2 for t, and then you'd have to work things out. So just be careful. But notice that I finished with the particular solution for S of t, and that's it. Okay, and now, for instance, it might even say, okay, according to all the work you've done, what's the position of the boat after 10 seconds? And so you would just do S of 10. So you could answer lots of questions now that you've got the particular solutions. Okay, this is similar. So what we're going to do is explain some things that you learned when you were in Algebra 2 and pre-calculus that your teachers didn't explain completely at that time. So if you throw a stone vertically upward, you throw it up and then let it peak and then fall back to the ground. If you know that you're tossing it from a position of 144 feet with an initial velocity of 96 feet per second, and we know that gravity has a pull or a force of negative 32 feet per second squared, of course that's your acceleration. Can you get to the position formula that you were asked to produce just right off the bat when you were in Algebra 2? In Algebra 2 and pre-calculus, we said memorize that if you're working in feet per second, that you start out with S of t equals negative 16t squared, then plug the velocity term in for the t, and then plug the initial height in at the end. And you all got used to that structure and just repeated that process. Now let's figure out why. Why does that work? So this is really cool. So all you have to go on is that A of t is negative 32. We know that that is the force of gravity on Earth. So how could I build from acceleration to velocity? You got it. Antiderivatives of both sides. Now, I'm going to do what I did on the last problem and call that C sub 1. And I notice that I can plug in at time 0 because it's initial time. So right when the problem starts, I notice that my velocity is 96 feet per second. That gives me that C sub 1 is 96. Now I can return to my velocity equation. So I'm reproducing so much of what I just did on the previous problem. So that's going to give me negative 32t plus 96. That's my particular solution for velocity. So what I want to do from here is, again, do the antiderivative of the left to get s of t. Do the antiderivative of the right, so t squared, and negative 32 divided by 2 is negative 16. Oh, that's why they told you to put that term in there. Plus 96t plus c sub 2 when I do the antiderivatives. Again, come back to the fact that you know that initially the position is 144 feet. So when time is 0, I have an initial position of 144. Again, the whole point of that is to show you that C2 is 144. So where am I now that I've done all this work? Well, S of t is going to be negative 16t squared plus 96t plus your C sub 2, which we just calculated at 144. And guys, that matches the equation you were trained to use when you were in Algebra 2 and Pre-Calculus. How cool is it that now you know why you were doing all that? I just think that's super neat. All right, so now that we have our position, acceleration, and velocity formulas, what length of time will the stone rise? There are two ways to do this. Method 1 is to take you all the way back to Algebra 2 and Pre-Calculus. Remember that the position equation indicates that your position graph is an upside down parabola, and so the stone's going to rise until it hits the vertex, and then it will begin to fall. So if you want to know for what length of time will the stone rise, find the time when it hits vertex. So just use the vertex formula. Well, what is the vertex formula? Well, x equals negative b all over 2a. X is t equals negative b all over 2a. So 2a would be negative 32, and if I'm not mistaken, that is going to be 3 seconds. So the stone will rise for 3 seconds. Now, instead of using Algebra 2 pre-calculus methods, remember you can always use what you already know about particle motion from calculus. And this is a physics concept that the stone's going to rise, 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 rise. And when it peaks, it stops for a split second in time, which means at that moment in time, its velocity is 0. So what's that mean to do? Set your velocity equation equal to 0 and solve for t. So my velocity equation is negative 32t plus 96 equals 0. And if you subtract 96 and divide by negative 32, you're going to get 3 seconds. So you can do that either way you want to do it, okay? So last but not least, and we are done. When and with what velocity will the stone hit the ground? So if the stone hits the ground, remember, its position is 0. So I'm going to go back to my handy-dandy position equation. And I've got plus 96t plus 144. Guys, I want to remind you on the calculator portion of the AP exam, you're allowed, once you say, hey reader, I'm solving this equation, you're allowed to just solve it on the calculator and show no work. We don't know what's going to happen with the AP exam this year, so let's pretend like this is on the no calculator part. So let's work through the algebra. First thing I notice is that all three terms are divisible by negative 16, so I'm going to do that to make my work easier. So negative 16t squared divided by negative 16. 96t divided by negative 16. 144 divided by negative 16. I'm checking my work just to make sure I'm not misfiring in my calculations. So that equation looks way easier. Well, darn, I was thinking it was going to factor, but no, I don't think it will. If it was minus 60 plus 9, I think it would. But since the 6 is even, I'm thinking I am taking or doing complete the square on this thing so I can take square roots of both sides of the equation. I'm going to add the 9 over. I know that half of 6 is 3. 3 squared is 9. Balance the equation, get 18. Take the square root of both sides and add 3. So I'm getting 3 plus or minus the square root of 18, which 18 is 9 times 2, 3 square root 2. Of course, the only time that makes sense then is 3 plus 3 square root 2, because 3 minus 3 square root 2 would be negative. So 3 plus 3 square root 2 seconds. If I do 3 plus 3 square root 2 on the calculator, that comes out to be approximately 7.2426 seconds. If I go back and say, okay, I'm going to let you use your calculator. If you want the velocity, then all you do, guys, is do v of 7.2426. You're going to plug that into your calculator, and you're going to get feet per second, and you're going to be done. So I'll leave it to you to do that on the calculator. I know you can. And we're going to stop here for today. So you'll start your practice work. At the end of the skeleton notes you have, you're going to see that we're going to do a little review of sequences and series. We'll do that tomorrow, and then you'll just continue this same practice set. But this way you can take a little mental break. All right, see you tomorrow, guys.